Welcome back, guys. In this teaching video, I'm looking at 3.7 hypothesis testing with the normal distribution part 1. 3.7 represents chapter 3 section 7 of the Pearson A level maths applied maths year 2 textbook. I'm going to start this teaching video by going through the key facts for this particular section. So we have that x follows a normal distribution with mean mu and variance sigma squared. The sample mean of x, denoted by x bar, follows a normal distribution with the same mean mu, but the variance changes. The variance is given by sigma squared over n, where n is equal to the sample size. This is the hypothesis that you follow if you're testing for an increase in the mean mu. This is the hypothesis that you follow if you're testing for a decrease in the mean mu. And finally, this is the hypothesis that you follow if you're testing for a change in the mean mu. So if it's increased in H1, you have more than. If it's decreased in H1, you have less than. If it's a change in H1, you have not equal to. One-tailed test, and this is a two-tailed test. Important facts. When you calculate your probability and it is less than the significance level, you reject H0 but you accept H1. If you calculate your probability and it is more than or equal to the significance level, you accept H0 but you reject H1. Here is exam style question 1. Daily mean wind speed is modelled as being normally distributed with a standard deviation of 3.1 knots. A random sample of 25 recorded daily mean wind speed is taken at Heathrow in 2015. Given that the mean of the sample is 12.2 knots, test at the 2.5% level of significance whether the mean of the daily mean wind speed is greater than 9.5 knots. The word greater is used. This indicates a one-tailed test. We're testing for an increase in the mean mu. So this is the hypothesis that we follow. In H1, we must have mu is greater than. Right, so before I start my solution, I'm going to take out all the key facts from the question. So here are my key facts. We are assuming that the mean mu is 9.5. So mu is equal to 9.5. Sigma, the standard deviation, is 3.1. The sample size n is 25. The significance level is 2.5%, which is equivalent to 0.025. Okay, so from the 25 recorded daily mean wind speeds, the sample mean was 12.2 knots. So we have that x bar, so lowercase x bar, is equal to 12.2. Right, so that's all of my key facts. Now I'm going to start the solution. Now, I always say to my students, whenever you have hypothesis testing questions, break your solution down into steps. So we're going to be looking at 6 basic steps. Step number 1, you define your random variable. So you pick a letter. I'm going to pick x. Let x be the daily mean wind speed. So that's step number 1 done. Step number 2, we're going to write down the distribution for x. We are told in the question that x follows a normal distribution. The mean is 9.5. The standard deviation is 3.1, hence the variance is 3.1 squared. That's the end of step number 2. Step number 3, we write down the distribution for the sample mean of x. It follows a normal distribution with the same mean. Okay, remember the mean stays the same, but the variance changes. It will be 3.1 squared divided by the sample size, 25. Okay, so that is the end of step number 3. Step number 4, you write down your hypotheses. H0, your null hypothesis. H1, your alternative hypothesis. So we are assuming that mu is equal to 9.5. We want to test if the mean is greater than 9.5. So in H1, we have mu is greater than 9.5. End of step 4. Step number 5, we proceed forward and we calculate our probability. So capital X bar. What do I put as my inequality? Well, I go back to my inequality in H1. It was greater than. So over here, I must use greater than or equal to. If in H1 it was less than, then over here you would use less than or equal to. Now the sample mean is given to be 12.2. So this is the probability that I want to calculate. Now remember, this probability represents an area. We're looking at a normal distribution. So that equal contributes to 0 area. So if you was not to include the equal, you will still get the same probability. So it doesn't really matter, but as a standard, if you've got greater than here, put greater than or equal to here. If you've got less than over here, put less than or equal to over here. Anyways, let's represent this area on a bell-shaped curve. So here is my bell-shaped curve. It is centered at the mean of 9.5. We have that 12.2 is on the right-hand side of 9.5, so it'll be somewhere over here. And what we're trying to calculate is the probability that capital X bar is greater than or equal to 12.2. So the area to the right of 12.2, this area over here. I'm going to rewrite this probability as follows. 12.2 is less than or equal to capital X bar, which is less than positive infinity. Now my lower limit is 12.2. So shorthand LL is 12.2. My upper limit, shorthand UL, I can't use infinity on my calculator. What I need to do is pick a number far more greater than 12.2. So you could pick 1000. The mean mu is equal to 9.5 and the standard deviation is equal to the square root of this. So square root of 3.1 squared over 25. Now some students make a common mistake. They take the square root of this over here. That is wrong because the distribution that you're interested in is the distribution for the sample mean of X, not X. Okay, so be careful. Take the square root of this. Right, we've got that there. Now we're going to use the normal CD function on our ClassWiz calculator and we're going to input these values in order to calculate this particular probability. So if I use my ClassWiz calculator and the normal CD function with these values, I get a probability which is equal to 0.000007 to 6 decimal places. Okay, now I need to compare this probability with the significance level. So my significance level is 2.5%. I see that this probability is less than. Okay, is less than 2.5%, which is 0.025. And for this reason, we have to reject H0 but accept H1. So we reject H0, accept H1. Our final step, step number 6, will be the conclusion. So in step number 6, we write a conclusion and it has to be in context. Now, if we're accepting H1, we are accepting that the mean has increased. So there is sufficient evidence. Okay, there is sufficient evidence at the 2.5% significance level that to finish off the sentence, you go back to the wording of the question. Mean of the daily mean wind speed is greater than 9.5 knots. Mean of the daily mean wind speeds is greater than 9.5 knots. And that there completes step number 6 and this particular exam style question. So these are the basic 6 steps. A quick highlight: step number 1, define your random variable. Step number 2, write down the distribution for X. Step number 3, write down the distribution for the sample mean of X. Step number 4, write down your hypothesis. Step number 5, calculate your probability, compare it with the significance level. And step number 6, write down a conclusion in context. So if you can follow these basic 6 steps, you've picked up a lot of marks on hypothesis testing in the exam. Here is exam style question 2. A certain brand of mineral water comes in bottles. The amount of water in a bottle in milliliter follows a normal distribution of mean mu and standard deviation 2. The manufacturer claims that mu is 125. In order to maintain standards, the manufacturer takes a sample of 15 bottles and calculates the mean amount of water per bottle to be 124.2 milliliter. Test at the 5% level whether or not there is evidence that the value of mu is lower than the manufacturer's claim. So the word lower indicates a one-tailed test. We are testing for a decrease in the mean mu. So this is the hypothesis that we follow. In H1, we have mu is less than for this exam style question. Now, before I start my basic 6 steps, I'm going to take out the key facts from the paragraph. So here are my key facts. The mean mu, we assume that is 125. The standard deviation sigma is 2. The sample size n is 15. We've got 15 bottles. The significance level is 5%, which is essentially 0.05. And we have that the sample mean lowercase x bar will equal 124.2 milliliter. This was the mean calculated from the sample 15 bottles. Okay, so these are my key facts. Now I'm going to proceed with the solution. Step number 1, we define our random variable. So I'm going to use the letter x. Let x be the amount of mineral water in a bottle. Okay, so that is the end of step number 1. Step number 2, x takes on a normal distribution according to the question with a mean of 125. The standard deviation sigma is 2, so the variance would be 2 squared. End of step 2. Now we can proceed to step number 3. We write down the distribution for the sample mean of x. So x bar follows a normal distribution with the same mean, 125. Okay, the mean stays the same, but the variance, ladies and gents, changes. It's no longer 2 squared, it's going to be 2 squared divided by the sample size, 15 bottles. End of step number 3. In step number 4, we write down the hypotheses, the null hypotheses, and the alternative hypotheses. So we're assuming that mu is equal to 125. We want to test if the mean has decreased. Has it gone lower than 125? So in H1, mu is less than 125. Right, so that's the end of step 4. Let's move on to step number 5. This is where you calculate a probability. So probability, capital X bar. In H1 we have less than, so over here we must use less than or equal to. Our sample mean from the 15 bottles was 124.2. So this is the probability that we're calculating. If you were to not include the equal, you will still get the same probability, because remember, this probability represents an area. We're looking at a normal distribution. So X bar equal 124.2 contributes to 0 area. But anyways, as a default, if it's less than over here, put less than or equal to here. If it's greater than here, put greater than or equal to here. You'll get your full marks. Anyways, what does this look like? Let's draw a bell-shaped curve. So here's my bell-shaped curve, centered at the mean 125. 124.2 is on the left-hand side of 125, so it'll be somewhere over here. We're trying to calculate the probability that capital X bar is less than or equal to 124.2. That's the area to the left of 124.2. So we can shade in that area. This is the area representing this probability. Let's rewrite this probability. So it will look something like this. Minus infinity is less than capital X bar, which is less than or equal to 124.2. Now the lower limit is minus infinity, but we can't type minus infinity into our calculator. So for the lower limit, we're going to take a number far more smaller than 124.2. So lower limit, LL, take it to be minus 1000. The upper limit, UL, is 124.2. The mean mu is equal to 125, and the standard deviation sigma is equal to the square root of this. Okay, so now we're going to use the normal CD function in our calculator with these values to calculate this probability. So if I use my ClassWiz calculator, I get the following answer to 4 decimal places: 0.0607. This is the probability that I must compare with my significance level, 5%. Notice that this probability is more than 5%, 0.05. So in this situation, when your probability is more than the significance level, you have to accept H0 but reject H1. So we accept H0 but we reject H1. We are rejecting the claim that the mean has decreased. So in our conclusion, this time we write there is insufficient evidence. Okay, so step number 6, conclusion in context. There is insufficient evidence at the 5% significance level that, go back to the wording of the question. Let's see. Value of mu is lower than the manufacturer's claim. The value of mu is lower than the manufacturer's claim. And that is the end of step number 6 and this particular exam style question. So, quick summary: step number 1, define your random variable. Step number 2, write down the distribution of x. Step number 3, write down the distribution of the sample mean of x. Step number 4, write down your hypotheses. Step number 5, calculate your probability, compare it with the significance level. And step number 6, write down your conclusion in context. So if you can follow these basic 6 steps, you can do any questions on hypothesis testing involving the normal distribution. Here is exam style question 3. So in this exam style question, I'm going to explain how to find the critical region. A machine produces bolts of diameter d where d has a normal distribution with mean 0.580 centimeter and standard deviation 0.015 centimeter. The machine is serviced, and after the service, a random sample of 50 bolts from the next production run is taken to see if the mean diameter of the bolts has changed from 0.580 centimeter. The word changed is used, which indicates a two-tailed test, and so the hypothesis will follow this format over here. In H1, we must have mu is not equal to, we are testing for a change in the mean, mu. The distribution of the diameter of bolts after the service is still normal with a standard deviation of 0.015 centimeter. Part A, find at the 1% level the critical region for this test. Okay, so what I'm going to do first of all is take out all the key facts from the paragraph. So here are my key facts. We've got the mean mu, which is 0.580. The standard deviation sigma is 0.015. The sample size n, we've got 50 bolts, so n is equal 50. The significance level is 1%. But because it's a two-tailed test, you need to divide it by 2. This gives us 0.5%, and this is equivalent to 0.005. Okay, so now let's proceed with the solution. Step number 1. We would usually define the random variable, but in this question, the random variable is already defined for us. We've got the letter D, which represents the diameter of the bolts. Okay, so in step number 1, I can straight away write down the distribution for D. So we are told that it follows a normal distribution. The mean is 0.580. The standard deviation is 0.015, hence the variance is 0.015 squared. End of step number 1. Step number 2, the distribution for the sample mean of D. Okay, it follows a normal distribution with the same mean. Remember, the mean stays the same. So 0.580. However, the variance changes. It will be 0.015 squared divided by the sample size, 50. End of step number 2. So in step number 3, we write down the hypotheses, the null hypothesis, and the alternative hypothesis. So in the null hypothesis, we're assuming that the mean mu is equal to 0.580. We are testing if the mean has changed. So in H1, we have mu is not equal to 0.580. Okay, On to step number 4. Now we're going to find two critical regions, the lower critical region and the upper critical region, because it's a two-tailed test. So here is my bell-shaped curve. So we've got the lower critical region over here and the upper critical region over here. We can call this critical value C1 and this critical value C2. This shading represents 0.005 and this shading over here also represents 0.005. Now LCR is a shorthand for the lower critical region. So my lower critical region will be D bar is less than or equal to C1. UCR is a shorthand for upper critical region. My upper critical region will be D bar is greater than or equal to C2. So let's work out C1. Now the area to the left is 0.005. The mean mu over here is 0.580. The standard deviation sigma is the square root of this. Remember, we take the square root of this, not the square root of this, because we want the standard deviation of the sample mean of D, not the standard deviation of D. So be careful. So square root of 0.015 squared over 50. Now to calculate C1, we have to use the inverse normal function on our class calculator. Now please remember, the inverse normal function is only used for the area to the left. So this area to the left is given. It's not a problem, so it's 0.005. Now, if I use my calculator, and specifically if I use the inverse normal function, I get that C1 is equal to 0.575 to 3 decimal places. Okay, so I've got my lower critical region LCR. That will be D bar is less than or equal to C1, which is 0.575. Let's move on to the upper critical region. So over here, let's see what area we take this time. This area is to the right. The inverse normal function is used for the area to the left. So we must do one take away this. That gives us 0.995. The mean mu is 0.580. The standard deviation sigma is square root of 0.015 squared over 50. And now we want C2, our second critical value. So we have to use the inverse normal function. So if I use the inverse normal function, my C2 value will be 0.585 to 3 decimal places. Okay, so my upper critical region, UCR, would be D bar is greater than or equal to C2, and my C2 is 0.585. That there, ladies and gents, is how you would find the critical region for hypothesis testing involving the normal distribution. This example was to find the critical region for a two-tailed test. Suppose you had a one-tailed test. To find the critical region, there are two different scenarios. Your one-tailed test would be a test for a decrease or for an increase. If your test is for a decrease, you're after the lower critical region. If your test is for an increase, you're after the upper critical region. Moving on to part B. The mean diameter of the sample of 50 bolts is calculated to be 0.587 centimeter. Comment on this observation in light of the critical region. So we have that lowercase d bar is equal to 0.587 centimeter. This over here is more than 0.585. So d bar equal to 0.587 falls in the upper critical region UCR, which is d bar is greater than or equal to 0.585. If a value falls in any critical region, upper or lower, what we need to do then is reject H0 but accept H1. So we are accepting the claim that the mean has changed. So we write a conclusion: there is sufficient evidence at the 1% significance level that the go back to the wording of the question. The mean diameter of the bolts has changed from 0.580 centimeter. And that there, ladies and gents, completes this particular exam style question and this teaching video. If you found the video useful, please don't forget to leave a comment, leave a like, turn on the notification bell so that you receive a notification every time I upload teaching videos. And please don't forget to subscribe.